This is the stable condition, where the metacenter is above the center of gravity. And this is the unstable condition, where the ship's center of gravity is above metacenter. When they are heeled by external forces to some angle, as the weight force and buoyancy force got separated, a righting lever or righting arm was created known as GZ. GZ or righting lever is the horizontal distance between the center of gravity, G, and the vertical line of action of buoyancy force. If moments are taken about the ship's center of gravity, G, in stable condition, there is a moment to return the ship to an upright position, since the righting lever was created on the low side. The weight force acts vertically downward on the high side, while the buoyancy force acts vertically upward on the low side, creating a moment that will bring the ship in upright position. This moment is called a moment of statical stability, known as the righting moment. In unstable conditions, when the ship is heeled at some angle, a capsizing lever is created at the high side of the ship. The weight force acts vertically downward through the center of gravity at the low side, while the buoyancy force acts vertically upward at the high side through the center of buoyancy, creating a moment that will tend the ship to heel further. This moment is called a capsizing moment. But this moment will not capsize the ship, it will only tend to heel the ship further until the ship's center of buoyancy is directly above the ship's center of gravity. In this state, the ship now is in neutral condition. Assuming that the ship is floating in still water without any external forces, she will remain in this position since no righting lever or capsizing lever exists. If there is no righting or capsizing lever, there is no moment that will bring back the ship to her upright position or no moment that would tend to heel her further. To determine the righting moment, it is GZ times ship displacement. In this case, the righting lever or GZ is 0, so the righting moment is also 0. That is why the ship will remain in this position if there are no external forces are applied. Now, the angle formed between the vertical line of force and the ship's centerline is called the angle of lull. If the ship is heeled further beyond the angle of lull by some external forces, the center of buoyancy moves further at the low side, creating a righting lever and righting moment that will bring back the ship at an angle of lull. If no external forces exist, she will come to rest at an angle of lull, not in an upright condition. In this condition, we can see that the ship will oscillate about the angle of lull. This is the formula to calculate the angle of lull. Where theta is the angle of lull, Gm is the negative initial metacentric height, and Bm is the Bm when the ship is upright. To calculate the righting lever or GZ at small angle of heel, this is the formula. For the large angle of heel, we will use the wall-sided formula to determine the righting lever. I will make a separate video on how to calculate the angle of lull and the righting lever at small and large angle of heel. At first glance, it seems that the ship is listing. But angle of lull is different from list. Let us compare these two conditions. List refers to the condition in which a vessel leans or tilts to one side, typically due to uneven distribution of weight or shifting cargo on board. Let's say, the ship is in stable condition, and we will add a weight to this side. The ship's center of gravity will move towards the center of gravity of the weight being loaded.
The biggest opportunity has written.
Of gravity is at G1, in which it is off the centerline. As a result, the ship is listing to where the new G is off the centerline. While at angle off lull, the ship's center of gravity is along the centerline, it is a result when the ship is in unstable condition. At an angle of lull, the ship may flop to either side, she will be heeled to starboard and will rest if there are no external forces exist. But if some external forces bring her to the other side, then she will heel to the other side and will remain in this condition if no external forces are applied. The ship will oscillate about the angle of lull, instead of her upright position. So the angle of lull may occur either on port or starboard, depending on the direction of the external forces. While in listing, the ship will only list to one side, towards the side where the ship's center of gravity is off the centerline. List is easy to correct compared to the angle of lull. In this case, we can add weight to the other side until the ship's center of gravity is along the centerline. Be sure that by doing these, you have calculated the ship's kg, since adding weight above the ship's center of gravity, the ship's g will rise. But for the angle of lull, you cannot do this. Adding weight on the high side when the ship is at angle of lull will worsen the situation. Let's say, we add a weight here. If she is heeled to the other side, suppose to be she will rest at an angle of lull. But since you have added weight on this side, the new position of ship's center of gravity will be off the centerline, causing the ship to heel further. Now you have two serious problems: the angle of lull still exists, and at the same time, the position of the ship's center of gravity is off the centerline. Calculations on the ship's stability are done before departure and anticipated arrival for the safety of the ship's entire voyage. But during the course of voyage, the ship's stability should be closely monitored as the angle of lull situation may arise. Here are several reasons that can cause the ship's center of gravity to rise above the metacenter during the course of voyage. Fuel and freshwater consumption, and their free surface effects. The effect of fuel and water consumption is a discharge of weight. If the tanks are below the ship's G, this will cause a rise in the ship's center of gravity, and an additional effect is the introduction of free surfaces due to tanks becoming partially filled. Next, ships carrying timber deck cargoes. This type of cargo absorbs moisture that will cause the ship's G to rise. A 15% allowance for the weight of the timber should be made when carried on deck in conducting stability calculations. Next is the ice accretion on deck. Sailing in higher latitudes usually encounters snowstorms, which will result in the accretion of ice on the deck, resulting in the rise of the ship's G above the metacenter. Another is the shift of the bulk cargo. The vertical component of a shift of solid bulk cargo may be enough to cause a rise in the ship's center of gravity. How to correct the angle of lull? First, determine whether it is an angle of lull or list. If you are not sure which of the two, then it is better to assume that it is an angle of lull. Take action to reduce the ship's kg by lowering the ship's center of gravity below the metacenter. If you have a wing tank which is full of ballast, empty it by discharging first the ballast on the high side. When it is emptied, then discharge the ballast on the low side. Another way to lower the ship's G is through ballasting. Select a subdivided double-bottom tank, and fill it with ballast water in this sequence. If it is divided into 3 compartments, start filling the tank on the low side. When the tank on the low side is completely full, start filling the center tank. If the center tank is full, fill the third tank which is on the high side. If all tanks are completely full, and the ship's center of gravity is below the metacenter, the ship will return to its upright condition. Another way to correct the angle of lull is to reduce the effect of free surfaces due to slack tank. Identify the slack tank below the ship's G and start topping up. This means filling those tanks until it is completely full to reduce the virtual rise of the ship's center of gravity.
Increases sufficiently to equal kg as shown. The angle of heel at which the above said inclination occurs is called the angle of lull. Normally, at the angle of lull, the vessel oscillates about its angle and returns to her angle of lull position. However, even though the vessel appears stable at this angle, this condition is dangerous and must be corrected. An unstable ship with an angle of lull could capsize. If proper precautions are not taken, it will continue to heel because If it is heeled by an external force, the ship will not come back to its original position. The steps you have to take to correct angle of loll are: A. Press up all slack tanks and lower weights if possible. B. Run up self water in the ballast tank water in the low side. C. After this tank is full, run up its counterpart on the high side. Repeat this action with other tanks until the ship becomes stable. D. If you are discharging or jettisoning cargo from the deck, discharge from the high side and make allowances for the shift of the vessel's G. E. If you are doing so with the ship gears, always
So what usually is the action that is required is we have to lower the center of gravity in order to get a positive GM. Okay, this is the action which is required for unstable equilibrium as well as neutral equilibrium. So we want the Km has to be greater than Kg. Km to be so all the conditions of your stable equilibrium is that what we are looking for. So how can we achieve this is when your vessel is at the angle of loll. Let's draw a vessel over here. This vessel is at her angle of loll. Okay, so what we are going to do is, in order to shift the center of gravity, what we can do is we can transfer the load distribution, bring the loads lower to the lower deck. Okay, now this is somewhat impractical, but it is possible. Okay, then loading of weights. In case you are loading weights, load the weights at the bottom or below the center of gravity in order to lower the center of gravity. Okay, so loading can be done in this way. What about in case the ship is at sea? What can be done is ballasting can be done. If you don't want to do loading in case the ship is at sea, so let's suppose these are your tanks, tank number 1, 2, 3. Okay, so how will you do ballasting is, so ballasting the tanks with the least moment of inertia, which are near the center line of the ship. So you will be ballasting the tank on the lower side first, which has the least moment of inertia. Okay, so this is the tank we will be ballasting first, then this tank, then you will be moving forward. Okay, then your number 3 tank, then the number 1 tank on the higher side. So this is how you are going to do loading of weights. What about discharging of weights? On discharging of weights, when you are discharging weights, you want to lower your center of gravity. So discharging of weights need to be from the higher side first. So in case weight is over here and over here, okay, now the vessel is heeled, so this distance is greater compared to this distance. Okay, so your center of gravity, we know the shift of center of gravity GG1 equals WD divided by W. So the vertical distance of the center of gravity is greater on the higher side compared to that on the lower side. Hence the center of gravity, the shift of GG1 would be greater when you will be doing the shifting the cargo from the higher side first. So discharge the cargo from the higher side first, okay, after which you can discharge the cargo from the lower side then. So this is how you are going to do the discharging. Then what about in case of jettisoning the cargo or you are removing the cargo